Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You are training models in Vertex AI by using data that spans across multiple Google Cloud projects. You need to find, track, and compare the performance of the different versions of your models. Which Google Cloud services should you include in your ML workflow? The options are Option A, Dataplex, Vertex AI Feature Store, and Vertex AI TensorBoard. Option B, Vertex AI Pipelines, Vertex AI Feature Store, and Vertex AI Experiments. Option C, Dataplex, Vertex AI Experiments, and Vertex AI ML Metadata. Option D, Vertex AI Pipelines, Vertex AI Experiments, and Vertex AI Metadata.
To arrive at the correct answer, we focus on the keywords, data that spans across multiple Google Cloud projects, find, track, and compare the performance, different versions of your models.
The correct answer is option C, Dataplex, Vertex AI Experiments, and Vertex AI ML Metadata.
Why is this correct? C. Dataplex securely manages data distributed across multiple projects. Vertex AI Experiments tracks and compares performance metrics across runs. Vertex AI ML Metadata tracks artifacts, lineage, and different versions of your models, fulfilling all requirements. Why are the others incorrect? A. Vertex AI Feature Store manages ML features, not cross-project data discovery. TensorBoard visualizes training metrics, but Dataplex is needed for cross-project data, and ML metadata is required for tracking model versions. B. Vertex AI Pipelines orchestrates workflows but doesn't manage cross-project data discovery like Dataplex. Feature Store serves ML features rather than tracking model performance versions, which requires experiments and ML metadata. Why are the others incorrect? D. Vertex AI Pipelines automates ML workflows but lacks the cross-project data management and discovery capabilities of Dataplex, which is explicitly needed for handling data that spans across multiple Google Cloud projects.
Your team is building an application for a global bank that will be used by millions of customers. You built a forecasting model that predicts customers' account balances 3 days in the future. Your team will use the results in a new feature that will notify users when their account balance is likely to drop below $25. How should you serve your predictions? The options are Option A, 1. Create a pub/subtopic for each user. 2. Deploy a cloud function that sends a notification when your model predicts that a user's account balance will drop below the $25 threshold. Option B, 1. Create a pub/subtopic for each user. 2. Deploy an application on the App Engine standard environment that sends a notification when your model predicts that a user's account balance will drop below the $25 threshold. Option C, 1. Build a notification system on Firebase. 2. Register each user with a user ID on the Firebase Cloud Messaging Server, which sends a notification when the average of all account balance predictions drops below the $25 threshold. Option D, 1. Build a notification system on Firebase. 2. Register each user with a user ID on the Firebase Cloud Messaging Server, which sends a notification when your model predicts that a user's account balance will drop below the $25 threshold.
To arrive at the correct answer, we focus on the keywords, millions of customers, notify users.
The correct answer is option D, 1. Build a notification system on Firebase. 2. Register each user with a user ID on the Firebase Cloud Messaging Server, which sends a notification when your model predicts that a user's account balance will drop below the $25 threshold.
Why is this correct? D. Firebase Cloud Messaging is the recommended, highly scalable service for cross-platform notifications to millions of users. It efficiently handles targeted message delivery without the massive architectural overhead of per-user topics. Why are the others incorrect? A. Creating a distinct pub/subtopic for each of the millions of users is an architectural anti-pattern causing severe quota issues. Pub/sub is not intended for direct end-user push notifications. B. Creating millions of pub/subtopics is an anti-pattern leading to unmanageable overhead and quota exhaustion. App Engine and pub/sub are less suited for mobile push notifications than Firebase. C. Notifying based on the average of all account balance predictions is logically incorrect. The business requirement dictates alerting individual users about their own specific account balances dropping below the threshold.
You are pre-training a large language model on Google Cloud. This model includes custom TensorFlow operations in the training loop. Model training will use a large batch size, and you expect training to take several weeks. You need to configure a training architecture that minimizes both training time and compute costs. What should you do? The options are: Option A, implement 8 workers of A2 megapoo 16G machines by using tf.distribute.multiworker mirrored strategy. Option B, implement a TPU pod slice with accelerator type equals v4l28 by using tf.distribute.tpu strategy. Option C, implement 16 workers of C2D HiKPU 32 machines by using tf.distribute.mirrored strategy. Option D, implement 16 workers of A2 HiKPU 8G machines by using tf.distribute.multiworker mirrored strategy.
To arrive at the correct answer, we focus on the keywords: large language model, custom TensorFlow operations, large batch size, minimizes both training time and compute costs.
The correct answer is option A, implement 8 workers of A2 megapoo 16G machines by using tf.distribute.multiworker mirrored strategy.
Why is this correct? A. Custom TensorFlow operations require GPUs since TPUs do not natively support them. The A2 megapoo 16G offers large GPU memory, at 180 GB, ideal for large batch sizes, and multi-worker mirrored strategy efficiently distributes the workload across multiple workers to minimize training time. Why are the others incorrect? B. TPUs do not support custom TensorFlow operations unless specifically ported to XLA, making this option technically infeasible for the given model. C. CPUs are too slow for large language model pre-training. Additionally, mirrored strategy is designed for multiple GPUs on a single worker, not across 16 separate workers. D. While it uses GPUs and the correct strategy, A2 HiKPU 8G provides only 40 GB of GPU memory. The A2 megapoo 16G with 80 GB is better suited for the large batch size required.
You work for a magazine distributor and need to build a model that predicts which customers will renew their subscriptions for the upcoming year. Using your company's historical data as your training set, you created a TensorFlow model and deployed it to Vertex AI. You need to determine which customer attribute has the most predictive power for each prediction served by the model. What should you do? The options are: Option A, stream prediction results to BigQuery. Use BigQuery's core x1, x2 function to calculate the Pearson correlation coefficient between each feature and the target variable. Option B, use Vertex Explainable AI. Submit each prediction request with the explain keyword to retrieve feature attributions using the sampled Shapley method. Option C, use Vertex AI Workbench user-managed notebooks to perform a lasso regression analysis on your model, which will eliminate features that do not provide a strong signal. Option D, use the what-if tool in Google Cloud to determine how your model will perform when individual features are excluded. Rank the feature importance in order of those that caused the most significant performance drop when removed from the model.
To arrive at the correct answer, we focus on the keywords, deployed it to Vertex AI, determine which customer attribute has the most predictive power for each prediction.
The correct answer is option B, use Vertex Explainable AI. Submit each prediction request with the explain keyword to retrieve feature attributions using the sampled Shapley method.
Why is this correct? The Vertex Explainable AI integrates directly with Vertex AI endpoints to provide local feature attributions for each individual prediction. The sampled Shapley method is a valid technique to compute how much each feature contributed to a specific prediction's outcome. Why are the others incorrect? A. Calculating Pearson correlation in BigQuery provides a global measure of linear association across the entire dataset, but it does not provide feature attributions for each individual prediction served. C. Lasso regression is a different model type used for feature selection during training, not a method for interpreting the feature attributions of an already deployed TensorFlow model for each prediction. Why are the others incorrect? D. The what-if tool is a visual interface for interactive exploration of model behavior, not an automated method for determining feature attributions for every individual prediction served by the model.
You are building a model to predict daily temperatures. You split the data randomly and then transformed the training and test datasets. Temperature data for model training is uploaded hourly. During testing, your model performed with 97% accuracy. However, after deploying to production, the model's accuracy dropped to 66%. How can you make your production model more accurate? The options are: Option A, normalize the data for the training and test datasets as two separate steps. Option B, split the training and test data based on time rather than a random split to avoid leakage. Option C, add more data to your test set to ensure that you have a fair distribution and sample for testing. Option D, apply data transformations before splitting, and cross-validate to make sure that the transformations are applied to both the training and test sets.
To arrive at the correct answer, we focus on the keywords: predict daily temperatures, split the data randomly, uploaded hourly, accuracy dropped.
The correct answer is option B, split the training and test data based on time rather than a random split to avoid leakage.
Why is this correct? B. For time series data like temperatures, randomly splitting the dataset causes future data to leak into the training set. Splitting chronologically ensures the model trains only on historical data, mirroring the production environment and preventing data leakage. Why are the others incorrect? A. Normalizing training and test sets separately is good practice, but it does not address the fundamental issue of randomly splitting time series data, which is the primary cause of the performance drop in production. C. Adding more data to the test set does not solve the underlying issue of data leakage caused by randomly splitting time series data, as the model would still learn from future information. D. Applying transformations before splitting causes data leakage by exposing full dataset statistics to the training phase, worsening the problem rather than fixing the temporal leakage issue.
You have a demand forecasting pipeline in production that uses Dataflow to pre-process raw data prior to model training and prediction. During pre-processing, you employ z-score normalization on data stored in BigQuery and write it back to BigQuery. New training data is added every week. You want to make the process more efficient by minimizing computation time and manual intervention. What should you do? The options are: Option A, normalize the data using Google Kubernetes Engine. Option B, translate the normalization algorithm into SQL for use with BigQuery. Option C, use the normalizer_fn argument in TensorFlow's feature column API. Option D, normalize the data with Apache Spark using the Dataproc connector for BigQuery.
To arrive at the correct answer, we focus on the keywords: data stored in BigQuery and write it back to BigQuery, minimizing computation time and manual intervention.
The correct answer is option B, translate the normalization algorithm into SQL for use with BigQuery.
Why is this correct? B. Translating the algorithm into SQL allows BigQuery to execute the normalization in place. This eliminates the need to move data to a separate compute service like Dataflow, significantly minimizing computation time and operational overhead. Why are the others incorrect? A. Moving computation to GKE introduces additional infrastructure to manage and still requires moving data out of BigQuery, contradicting the goal of minimizing manual intervention and computation time. C. Using TensorFlow's feature column API applies normalization during model training or serving, not as a persistent data preprocessing step in BigQuery, altering the pipeline structure and potentially increasing training time. D. Using Apache Spark on Dataproc adds unnecessary infrastructure complexity and requires moving data between BigQuery and Dataproc, which is less efficient than performing the calculation directly within BigQuery using SQL.
You are responsible for building a unified analytics environment across a variety of on-premises data marts. Your company is experiencing data quality and security challenges when integrating data across the servers, caused by the use of a wide range of disconnected tools and temporary solutions. You need a fully managed, cloud-native data integration service that will lower the total cost of work and reduce repetitive work. Some members on your team prefer a codeless interface for building extract, transform, load, ETL, process. Which service should you use? The options are: Option A, Dataflow. Option B, Dataprep. Option C, Apache Flink. Option D, Cloud Data Fusion.
To arrive at the correct answer, we focus on the keywords: fully managed, cloud-native data integration service, codeless interface for building extract, transform, load, ETL, process.
The correct answer is option D, Cloud Data Fusion.
Why is this correct? D. Cloud Data Fusion is a fully managed, cloud-native data integration service that provides a graphical, codeless interface for building ETL pipelines, perfectly matching the team's requirements. Why are the others incorrect? A. Dataflow is a fully managed service for stream and batch processing but requires writing code in Apache Beam, lacking a codeless interface. B. Dataprep focuses on data exploration, cleaning, and preparation rather than being a full-scale, codeless data integration service for building end-to-end ETL pipelines. C. Apache Flink is an open-source distributed stream processing framework, meaning it is neither a fully managed service nor does it provide a codeless interface natively.
You recently used BigQuery ML to train an AutoML regression model. You shared results with your team and received positive feedback. You need to deploy your model for online prediction as quickly as possible. What should you do? The options are: Option A, retrain the model by using BigQuery ML, and specify Vertex AI as the model registry. Deploy the model from Vertex AI model registry to a Vertex AI endpoint. Option B, retrain the model by using Vertex AI. Deploy the model from Vertex AI model registry to a Vertex AI endpoint. Option C, alter the model by using BigQuery ML, and specify Vertex AI as the model registry. Deploy the model from Vertex AI model registry to a Vertex AI endpoint. Option D, export the model from BigQuery ML to cloud storage. Import the model into Vertex AI model registry. Deploy the model to a Vertex AI endpoint.
To arrive at the correct answer, we focus on the keywords: BigQuery ML, deploy your model for online prediction as quickly as possible.
The correct answer is option C, alter the model by using BigQuery ML, and specify Vertex AI as the model registry. Deploy the model from Vertex AI model registry to a Vertex AI endpoint.
Why is this correct? C. Using the alter model statement in BigQuery ML to register an existing model with Vertex AI model registry is the fastest approach. It avoids retraining or exporting, directly enabling deployment to a Vertex AI endpoint. Why are the others incorrect? A. Retraining the model takes additional time and compute resources, which is unnecessary since it has already been trained and validated. B. Retraining the model in Vertex AI is time-consuming and redundant since you already have a satisfactory trained model in BigQuery ML. D. Exporting the model to cloud storage and importing it manually into Vertex AI model registry takes longer and involves more steps than using alter model.
Your team is experimenting with developing smaller, distilled LLMs for a specific domain. You have performed batch inference on a dataset by using several variations of your distilled LLMs and stored the batch inference outputs in cloud storage. You need to create an evaluation workflow that integrates with your existing Vertex AI pipeline to assess the performance of the LLM versions while also tracking artifacts. What should you do? The options are: Option A, develop a custom Python component that reads the batch inference outputs from cloud storage, calculates evaluation metrics, and writes the results to a BigQuery table. Option B, use a Dataflow component that processes the batch inference outputs from cloud storage, calculates evaluation metrics in a distributed manner, and writes the results to a BigQuery table. Option C, create a custom Vertex AI pipelines component that reads the batch inference outputs from cloud storage, calculates evaluation metrics, and writes the results to a BigQuery table. Option D, use the automatic side-by-side (AutoSXS) pipeline component that processes the batch inference outputs from cloud storage, aggregates evaluation metrics, and writes the results to a BigQuery table.
To arrive at the correct answer, we focus on the keywords: batch inference outputs in cloud storage, create an evaluation workflow that integrates with your existing Vertex AI pipeline, tracking artifacts.
The correct answer is option D. Use the automatic side-by-side (AutoSXS) pipeline component that processes the batch inference outputs from cloud storage, aggregates evaluation metrics, and writes the results to a BigQuery table.
Why is this correct? D. The automatic side-by-side (AutoSXS) pipeline component is a managed Vertex AI tool designed to evaluate and compare the performance of multiple LLM versions natively, automatically calculating metrics and seamlessly tracking artifacts. Why are the others incorrect? A. A custom Python component requires manually implementing metrics calculation and artifact tracking, increasing operational overhead compared to using a managed LLM evaluation component. B. A Dataflow component adds unnecessary infrastructure complexity for this task and lacks native, built-in integration with Vertex AI pipeline's artifact tracking capabilities. C. Building a custom Vertex AI pipelines component requires significant development and maintenance effort to replicate the out-of-the-box LLM evaluation and comparison features provided by AutoSXS.
You have developed a custom ML model using Vertex AI and want to deploy it for online serving. You need to optimize the model's serving performance by ensuring that the model can handle high throughput while minimizing latency. You want to use the simplest solution. What should you do? The options are: Option A, deploy the model to a Vertex AI endpoint resource to automatically scale the serving backend based on the throughput. Configure the endpoint's auto-scaling settings to minimize latency. Option B, implement a containerized serving solution using Cloud Run. Configure the concurrency settings to handle multiple requests simultaneously. Option C, apply simplification techniques such as model pruning and quantization to reduce the model size and complexity. Retrain the model using Vertex AI to improve its performance, latency, memory, and throughput. Option D, enable request response logging for the model hosted in Vertex AI. Use Looker Studio to analyze the logs, identify bottlenecks, and optimize the model accordingly.
To arrive at the correct answer, we focus on the keywords: custom ML model using Vertex AI, deploy it for online serving, handle high throughput while minimizing latency, simplest solution.
The correct answer is option A. Deploy the model to a Vertex AI endpoint resource to automatically scale the serving backend based on the throughput. Configure the endpoint's auto-scaling settings to minimize latency.
Why is this correct? A. Vertex AI endpoints provide a fully managed and simple solution for online serving. Configuring auto-scaling settings directly addresses the need to handle high throughput while minimizing latency without the operational overhead of managing underlying infrastructure. Why are the others incorrect? B. Cloud Run requires implementing and managing a containerized serving solution, which is more complex than using the native, fully managed Vertex AI endpoint. C. Applying pruning and quantization involves modifying and retraining the model, which adds significant complexity and violates the requirement for the simplest solution. D. Logging and analyzing with Looker Studio helps identify bottlenecks but does not inherently optimize the serving infrastructure to handle high throughput or minimize latency.
You are a lead ML architect at a small company that is migrating from on-premises to Google Cloud. Your company has limited resources and expertise in cloud infrastructure. You want to serve your models from Google Cloud as soon as possible. You want to use a scalable, reliable, and cost-effective solution that requires no additional resources. What should you do? The options are: Option A, configure compute engine VMs to host your models. Option B, create a Cloud Run function to deploy your models as serverless functions. Option C, create a managed cluster on Google Kubernetes Engine, GKE, and deploy your models as containers. Option D, deploy your models on Vertex AI endpoints.
To arrive at the correct answer, we focus on the keywords: limited resources and expertise in cloud infrastructure, serve your models from Google Cloud as soon as possible, scalable, reliable, and cost-effective solution, requires no additional resources.
The correct answer is option D, deploy your models on Vertex AI endpoints.
Why is this correct? D. Vertex AI endpoints provide a fully managed, scalable service specifically designed for serving ML models, requiring zero infrastructure management, aligning perfectly with limited resources and expertise. Why are the others incorrect? A. Compute engine VMs require manual provisioning, configuration, and ongoing management, which contradicts having limited resources and infrastructure expertise. B. Cloud Run functions have deployment package size and execution time limits, making them less suitable and harder to optimize for complex ML model serving than managed ML services. C. GKE requires significant cloud infrastructure expertise to configure and manage the Kubernetes cluster, violating the constraint of limited resources and expertise.
You work at an organization that manages a popular payment app. You built a fraudulent transaction detection model by using scikit-learn and deployed it to a Vertex AI endpoint. The endpoint is currently using one E2 standard 2 machine with 2 vCPUs and 8 GB of memory. You discover that traffic on the gateway fluctuates to 4 times more than the endpoint's capacity. You need to address this issue by using the most cost-effective approach. What should you do? The options are: Option A, redeploy the model with a TPU accelerator. Option B, change the machine type to E2 HiCP32 with 32 vCPUs and 32 GB of memory. Option C, set up a monitoring job and an alert for CPU usage. If you receive an alert, scale the vCPUs as needed. Option D, increase the number of maximum replicas to 6 nodes, each with one E2 standard 2 machine.
To arrive at the correct answer, we focus on the keywords: scikit-learn, Vertex AI endpoint, traffic on the gateway fluctuates to 4 times more, most cost-effective approach.
The correct answer is option D, increase the number of maximum replicas to 6 nodes, each with one E2 standard 2 machine.
Why is this correct? D. Setting the maximum replicas enables built-in autoscaling for the Vertex AI endpoint. It automatically scales out during traffic spikes and scales in when traffic drops, providing the most cost-effective solution for fluctuating traffic. Why are the others incorrect? A. Scikit-learn models typically run on CPUs, not TPUs. TPUs are specialized for deep learning workloads, like TensorFlow/PyTorch. Redeploying with a TPU would be unnecessarily expensive and potentially incompatible. B. Vertically scaling to a permanently large machine is not cost-effective for fluctuating traffic. You would pay for maximum capacity continuously, even during periods of low traffic. C. Relying on manual scaling via alerts introduces unnecessary operational overhead and delays. Vertex AI already provides built-in autoscaling to dynamically and automatically adjust resources based on traffic.
You are building a MLOps platform to automate your company's ML experiments and model retraining. You need to organize the artifacts for dozens of pipelines. How should you store the pipeline's artifacts? The options are: Option A, store parameters in Cloud SQL and store the model's source code and binaries in GitHub. Option B, store parameters in Cloud SQL, store the model's source code in GitHub, and store the model's binaries in cloud storage. Option C, store parameters in Vertex ML metadata, store the model's source code in GitHub, and store the model's binaries in cloud storage. Option D, store parameters in Vertex ML metadata and store the model's source code and binaries in GitHub.
To arrive at the correct answer, we focus on the keywords: MLOps platform, ML experiments, model retraining, organize the artifacts, store the pipeline's artifacts.
The correct answer is option C, store parameters in Vertex ML metadata, store the model's source code in GitHub, and store the model's binaries in cloud storage.
Why is this correct? C. Vertex ML metadata is specifically designed for ML experiment tracking and artifact lineage. GitHub is best for source code version control, while cloud storage provides scalable object storage for large model binaries. Why are the others incorrect? A. Cloud SQL is not an optimized ML metadata store, and GitHub is inappropriate for storing large model binaries, which require scalable object storage. B. Cloud SQL lacks built-in ML lineage and experiment tracking features. Vertex ML metadata is the purpose-built service for managing ML parameters and artifacts. D. While Vertex ML metadata is correct for parameters, GitHub is designed for text-based source code, not for storing large binary files like models.
Your team frequently creates new ML models and runs experiments. Your team pushes code to a single repository hosted on cloud source repositories. You want to create a continuous integration pipeline that automatically retrains the models whenever there is any modification of the code. What should be your first step to set up the CI pipeline? The options are: Option A, configure a cloud build trigger with the event set as pull request. Option B, configure a cloud build trigger with the event set as push to a branch. Option C, configure a cloud function that builds the repository each time there is a code change. Option D, configure a cloud function that builds the repository each time a new branch is created.
To arrive at the correct answer, we focus on the keywords: cloud source repositories, continuous integration pipeline, automatically retrains the models whenever there is any modification of the code.
The correct answer is option B, configure a cloud build trigger with the event set as push to a branch.
Why is this correct? B. Cloud Build is the native CI/CD service for GCP. A push to a branch trigger directly satisfies the requirement to automatically run the pipeline whenever there is any modification of the code. Why are the others incorrect? A. A pull request trigger only runs on PR events and would misdirect code pushes to branches, failing to capture all code modifications. C. While possible, using cloud functions is an anti-pattern here. Cloud Build is the purpose-built, managed CI/CD service that natively integrates with cloud source repositories. D. Triggering only on new branch creation misses regular code commits to existing branches. Additionally, Cloud Build is preferred over cloud functions for CI pipelines.
You need to develop a custom TensorFlow model that will be used for online predictions. The training data is stored in BigQuery. You need to apply instance-level data transformations to the data for model training and serving. You want to use the same pre-processing routine during model training and serving. How should you configure the pre-processing routine? The options are: Option A, create a BigQuery script to pre-process the data and write the result to another BigQuery table. Option B, create a pipeline in Vertex AI pipelines to read the data from BigQuery and pre-process it using a custom pre-processing component. Option C, create a pre-processing function that reads and transforms the data from BigQuery. Create a Vertex AI custom prediction routine that calls the pre-processing function at serving time. Option D. Create an Apache Beam pipeline to read the data from BigQuery and pre-process it by using TensorFlow Transform and Dataflow.
To arrive at the correct answer, we focus on the keywords: TensorFlow model, online predictions, instance-level data transformations, same pre-processing routine during model training and serving.
The correct answer is option D. Create an Apache Beam pipeline to read the data from BigQuery and pre-process it by using TensorFlow Transform and Dataflow.
Why is this correct? D. TensorFlow Transform is specifically designed to solve train-serving skew by exporting a pre-processing graph alongside the model. This guarantees the exact same transformations are applied during both Dataflow-based training and low-latency online serving. Why are the others incorrect? A. BigQuery is optimized for batch processing. BigQuery scripts cannot be invoked during real-time online serving, which would result in train-serving skew. B. While Vertex AI pipelines can pre-process training data, it does not inherently package the pre-processing logic with the model for seamless, consistent use during online serving. C. A custom prediction routine handles serving time pre-processing but requires you to separately maintain and run the training pre-processing logic, risking train serving skew compared to the unified TF transform approach.